A big welcome to economist Robin Hanson during this festive season. Why don't the aliens celebrate Christmas? Because they don't give away their presents. So where are all the aliens? I mean, the universe is 13.8 billion years old. Should we expect it to be lit up like a Christmas tree? Perhaps the aliens exist in a space-time too far away for us to detect right now. So today we'll be discussing aggressive alien civs and how far away they may be in space and time. And so the topic was recently explored in detail on Overcoming Bias, Robin's blog. So on the Science, Technology in the Future channel, Robin and I have covered a wide variety of topics before, but most relevant to today's theme are the interviews on the Great Filter and Burning the Cosmic Commons. So if you want some context, please watch those as well. So first of all, I'll let you take the reins here.
This is going to be difficult. This is the first time I've talked with this about to anybody, because this is only a few weeks old as an insight. And I'm going to rely on my interviewer here, Adam, here to help me explain it to you, because if he doesn't understand, he'll push further to help you understand. So, as you may know, there might be aliens out there. If the universe is spatially infinite, there almost surely are them somewhere out there, but they might not be in our observable universe, and they might not even be in the observable universe that we will ever see, because with dark energy and exponential expansion, there's only actually a limited amount of the space that we could ever see. So the usual framing of this discussion is something like the Drake equation. You say, well, gee, how hard is it to produce something like us? And you walk through a set of steps. Well, first you'd need a star, and then you need a planet, and then it would need to be in the right orbit, and then it might need the right size, and maybe with the right kind of star. And then, life would have to start somehow, and then it would have to eventually move to more complicated life, and then there might be intelligence and civilization, and then how long would that last? You estimate a whole bunch of numbers, and you multiply them all together, and you say, this is, on average, how many alien civilizations there are per star. Therefore, multiply that by the number of stars in the galaxy. Then you'd say, here's the number of alien civilizations in the galaxy. And you can get high numbers, millions of them, or you can get really low numbers, none whatsoever in the entire visible universe. Those are all consistent with, a wide range of estimates on these numbers. And that's the usual debate, and that's where it usually sits. We're arguing about where we sit on these wide range of numbers. So I'm proud, I think, to be able to say I have a different way of doing this analysis that lets us give a pretty definitive answer to how far away are the nearest aliens. So I'm going to have a simple model I'm going to outline here, and it just has 3 parameters. And each of these parameters we know to roughly within an order of magnitude, i.e. a factor of 10. So if you buy this model and you plug in our estimates within a factor of 10, you can get, within a factor of 10 or 20 estimate of how far away are the nearest aliens. Mm-hmm. And that's a much more definitive answer than we had before. And so that's what I want to walk through here, this argument for this model.
Okay. So what's the alternative to the Drake equation? And do you have a name for it yet?
Not other than the Great Filter sort of applied to how far away are aggressive aliens. So I am going to say I have a model of aggressive aliens. They aren't a model of all possible aliens. So in some sense, if there are other kinds of aliens that are just completely independent from these kind, then my model doesn't say much about them.
Are these aggressive aliens similar to the aliens you describe in your Burning the Cosmic Commons thesis?
Yes. So there's really just 2 key features of these aliens. One is they expand. They expand out from their initial point where they arise soon and relatively fast. So there's some expansion rate that they do. So at that expansion rate, they might try to make it as close to the speed of light as possible. They can't get there. Maybe they could get up to half or a tenth of the speed of light. I don't know. But that's roughly the uncertainty of this parameter. One of the key parameters in the model is aggressive alien species expand from their point of origin. The second thing to know about an aggressive alien species is it prevents other aggressive alien species within its zone of control. So we think we have a chance of becoming an aggressive alien species. We disagree about whether that's a good idea, and I'm not here to argue about that today. But it looks like we have the inclination such that we might become one. That is, in the near future, if we don't kill ourselves, we might spread out, and then internal competitive forces might push us outward in a faster and faster race until we were expanding out at the fastest rate we could manage. And as we expanded out, we would grab stuff and then start to use it as best we can, and that would probably prevent another sort of alien species from appearing after we arrived. That is, if there was primitive life there, we might isolate it, put it in a zoo, etc., but we wouldn't let it grow up to become an expanding civilization that expanded from that point. Mm-hmm. So that's the two key definitions here. An aggressive alien species is one that expands and then prevents others from doing the same thing when it's within its sphere of control. So now it might allow others in a sphere of control in a zoo or something, but a key assumption in the analysis is we are not now in the sphere of control of an alien aggressive civilization. They aren't locking us down now and preventing us from expanding. We could potentially expand. And that makes our date of origin, i.e. near the current moment of 13.8 billion years after the origin of the universe, a plausible date of when aggressive alien species start. It's a sample from that distribution. It's just a sample of one, but that's actually enough information to give us that key parameter to within order of magnitude. And we'll talk a bit about what that means. Okay, so my model has three parameters. Mm-hmm. First parameter is there's this definition of an aggressive alien species. The second is there's the speed at which it expands. Mm-hmm. Third is sort of the average rate at which they appear in some sense, or the average rate at which how hard it is. And that's going to be set by this one data point we have of we arrived at 13.8 billion years. So if we're a random sample from the set of potentially aggressive alien species, civilizations, and we arrived at 13.8 billion years, then we could think of that as a sample from the distribution of those arrival times. The third and last parameter is the one that's going to take longer to explain here, which is why I left it for last, which is the number of hard steps in the great filter.
Right. Yep.
So let's walk through what that means.
Yes. Good.
So the great filter is whatever it is that makes it hard for some part of the universe to start out early on with simple dead matter and then eventually end up with something that starts producing this aggressive alien civilization. It has to originate life, and then more complicated life, and then multicellular life, and then intelligence, etc. And it has to go through many steps that are hard. And what we mean by hard is to say, well, if we think about each step, some local region of the universe got to that step, and now it's trying to make the next step, and it basically just keeps trying. And it takes a long time to succeed, and we can talk about the expected time for that success. How long would that take on average? And the idea is for a lot of these steps, that expected time is really long. In fact, much longer than the time we've seen so far, 13.8 billion years. That is, on any one small planet or oasis out there, the chance of it having reached this origin point of starting an aggressive alien civilization is very small by this point in time, which is basically the fact that the universe looks empty. So the fact that we look out there, we hardly see anything, tells us that for each small part, the chance is very small that it started an aggressive alien civilization in the last moment we could see it, because we don't see big aggressive alien civilizations out there. And that suggests that, in fact, this chance is very low. So the key point is we can assume that there's a set of steps that each place has to go through. The total chance of getting through all those steps by the deadline of our moment of 13.8 billion years is low. And that's the great filter. And we actually can say something very precise and interesting about what that means about the chance of things happening at different times. So if you have a set of steps that a system has to go through, and at each step the chance is very low, we'll start out, say, assume that chance is constant per time, but we're going to be able to generalize that. Then the chance that it goes through all the steps by any one time deadline is proportional to that time to the power of the number of steps. So if there's 3 steps, it's proportional to that time raised to the 3rd power. If there's 10 steps, it's proportional to that time raised to the 10th power. And the idea is this doesn't just to apply to a place like Earth, it applies to sort of any volume of space starting at the beginning of the universe and projecting forward into the future. That is, each volume of space could have planets or things in it, stars in it. They might start at different times or end at different times, but still the integral over all the chances of different things producing an aggressive alien civilization is proportional to time raised to this power of n, the number of steps.
N minus 1. Is this exemplified in your diagram? Is this what your diagram is about?
Well, my diagram allows me to say interesting things with that, and so I'm happy to sort of point you to it. I don't want to bury you too much in complicated math all at once, but the key idea before I introduce the diagram is to say that this time raised to the power n factor lets us be relatively precise about where the aliens are. So you might think, well, this is showing that the time dependence has a certain form. How does it tell you anything about how far away they are? And so the remarkable thing is to say, no, there is a connection between how far away they are and how fast they appear. And so that's where I'm going to introduce this diagram. And now I'm going to do a screen share where I find it. All right, so now we are looking at this diagram. And this is a space-time diagram. The x-axis is space. It's one dimension we're showing. And the y-axis is time. And we are imagining there are multiple civilization origins at these blue dots. And we're, for simplicity, assuming that they all happen at the same time and at a certain spatial separation. So this isn't exactly right, but it's going to give us, say, within an order of magnitude estimate of what's going on here. So the key idea is that this civilization origin creates this expanding region that goes out as this V upward. And in that expanding region, new civilizations are precluded. That is, another aggressive civilization can't exist up above those lines because this civilization's already taken over that region. And if we space these civilizations out, you can see these V-shaped regions hit a top point, and that limits the total space where any new civilization could appear. So this yellow shaded region is now a representative region of the sort where a new civilization could appear. It can only appear after time 0, and it has to appear before this deadline of where this civilization wave passes through. And all of the other regions in the X space are other copies of this shape. All the other regions are just so. This one shape is repeated over and over again to the left and to the right. So this shape we can integrate over, and we get a distribution of the chances by integrating t to the n over this region, yellow region, as we see it. That integral will have a median of its distribution. There'll be a middle point in that distribution. And the key working of this model is to say, what if we assume that this blue dot is at the middle of that distribution, or near the middle of that distribution? So that's typically where the blue dot will be. If so, that's going to set a constraint on this spatial distance, the width of this box on the x-axis, relative to the height. So there's a little math here I'm showing, which is the actual math representing that constraint, and R here at the beginning is the rank order of this civilization in this distribution. So if the rank is a half, then 1 over R minus R is just 1. And so the key idea here is we have a simple consistency relation, at least here in one dimension, that says if the distribution of civilization origin times was constrained to be somewhere within this region of the shape, and that region was set by the median of the distribution, then we have a way to calculate this distribution here mathematically that actually tells us what the relationship is between the average time at which these civilizations appear and the average spatial distance between them. And so I've plugged these numbers in, done this math here and done numerical solutions. And basically, we can find that the answer here of how far away they are depends a lot on the power n. So, but first let's just talk about the time. So the universe that we're in is 13 billion years old, and that seems like it's old, but we know that the universe we're in could last for trillions of years more. And in fact, we know that there are stars around us that could last for trillions more. At least, well, it could last for that. The question is, how long could it last such that alien civilizations could appear later on?
Yep.
So it looks like this is not the deadline. So we are actually pretty early, which is a problem for the theory that we're alone. So if we were alone, if we didn't show up, nobody would show up. If the chances for anybody to show up were really, really low, then we should show up somewhere in the middle of the time distribution of when anyone could show up. But we are really early with respect to that distribution. We have shown up at only 13.8 billion years when we could have shown up trillions of years from now. Now, the way that we're going to explain that is to say, well, there's a deadline. We had to show up before the deadline. Then you say, well, what's the deadline? People have often talked in terms of, well, Earth has a deadline in the sense that the sun will go supernova, will get really big and burn up the Earth, and therefore life on Earth had to appear before that deadline. And that's true, but there are lots of other stars out there with lots of longer lifetimes, and Earth isn't the only star, and new stars will appear later. So the more fundamental deadline we're positing here is to say that eventually alien civilizations show up, and eventually they take over all the space, and that means we can't show up later than that because they will preclude it. And so we have shown up 13.8 billion years after the beginning of the universe, and so our date is then a random draw, we would say, from this distribution of origin times. And it's therefore telling us about the height of this diagram. Telling us about, on average, how long can you wait until the time's up. And this formula then relates that to the distance to the alien civilizations via the speed of the expansion and this power. Now, if the speed of the expansion here, could be a tenth of the speed of light, maybe a hundredth, or maybe the whole speed of light, somewhere in that range. But in a sense, this diagram doesn't care. So our estimates of how far away the nearest alien species will be modulo an estimate of the expansion speed. So, we won't be very certain about that. But other than that, we can say a lot. So let me switch you to a different diagram here now. Sorry, move over here. This is a diagram of a more realistic model, but still in one dimension. So let me walk you through this model. Again, x-axis is space, y-axis is time. Now we're going to have civilizations show up randomly in proportion to that t to the n, and here I picked n equals 10. 10 hard steps, and we can come back to how plausible n of 10 is. And given that n is 10, there's going to be, I have some speed, and you can see that this is sort of a jagged diagram, and at the bottom of each V is where a civilization starts. So you can even see my mouse there, I guess, near the bottom of one. The earliest civilization starts, and then you can see it expands outward at my assumed expansion speed. And then its wave of influence eventually meets the wave of influence of some other civilizations who started out at some other point. And then relatively soon, everything is taken up and there's no more room for anything to start. So I want to call your attention to a couple of features in this diagram. So this was actually created by sampling according to that power law of time, and then modeling the fact that it expands, and then modeling the fact that if it expands, nothing else can appear in that region. And I hope to soon, show you three-dimensional versions of this, but this is a simple version in one dimension. So one thing to notice here is they appear within a relatively short time of each other. The universe is empty for a long time, and all of a sudden they all show up. And that's driven by this power of 10. The power of 10 really concentrates their appearance all in a relatively short period, because the power of 10 is growing very quickly. When you double time by a factor of 2, the power of 10 goes up by a factor of 1,000. And so that means there comes a point where they just start showing up fast and fast and fast. And if you think of there like being some region of space left available, the probability of an alien civilization showing up will be higher toward the higher spaces of those regions left. And that means near these peaks of the V's, you're going to have a lot of things showing up. And so you can see near the top of these peaks, there's a lot of jagged things just before the top of the peaks, because a lot of civilizations are showing up just at the last possible minute, because there's a little narrow space available for them, and t to the n is really pushing. And so there's a very sort of a fractal distribution here almost of the civilizations. There's a relatively few widely separated initial origins, and then the later origins are all concentrated in the little gaps remaining up near the top, where they're actually spaced pretty close to each other. So in this analysis here, for example, there are 75 civilization origins across this spacing here. And, if you say, that's the average spacing here compared to the speed, and say this was near the speed of light, then you might say, well, that would predict that on average, civilizations are about 1 billion light years apart. And then that means that, you might meet one in 500 million years if you were traveling at the speed of light, which is a pretty long way apart. But of course, since we'll probably last for another 100 billion years before we separate from each other and can't see each other, there'll be this period of time from 1 billion years from now to 100 billion years from now where we'd have contact with lots of alien civilizations and could exchange information and travel and visit and things like that. So that's an interesting future era to think about. But still, it doesn't start for 1 billion years from now. But that's the average of this distribution. But this is a highly skewed distribution. And so that's the interesting thing to notice here. If you look at, say, the closest 10% of the distribution, say what happens if we were, that lucky to be, and our closest alien is only 10% of other aliens have another alien that close. How close would they be then? Well, now you're talking 30 million years till you meet them. And that's much closer. But it's still, of course, a long way away in terms of our history. Our descendants are going to vastly evolve and change in the next 30 million years.
Right.
But still, I'm going to end this sharing because I think that's enough for there.
Okay.
So for some people, it's not very intuitive that it should be this power of n. And so clearly, I'm getting these mathematically precise answers because I'm assuming this power of n is that power of n. It's that function. It's not some other function. And you might say, well, how could I be so sure that that's the right function? Now, but again, there's only three parts to this model. They expand at the speed of light. There's that they constrain each other, and that they appear proportional to t to the n. Mm-hmm. So you might look at t to the n and go, if I'm going to question your model, that's where I got to question it. That's where I got to doubt. I got to say, okay, I believe that aliens prevent other aliens within their sphere of control from arising. I believe they expand at some, rate less than the speed of light. Why should I believe t to the n? You might say that. So I want to convince you now that t to the n is actually something we know pretty well, and it's pretty robust. And so I want to walk you through arguing for that. And give you some conceptual thing, and then I could give the diagram as support for that. But that's what this part of the discussion is. It's like, why should you believe t to the n? And why should you believe n is high? Why maybe n is 1 or 1 or 2 or something? In which case, we get a different picture here.
Right.
All right.
But you believe that it's probably high because
yes.
We've appeared so early in the timeline?
No, that's actually not the reason. So we could have appeared very early even with a low power.
Sure.
Although we might have a higher chance of seeing other alien civilizations off there. So if the ratio of the speed of expansion to the speed of light is high, in the sense that, they don't expand nearly as fast as the speed of light, then there's a higher chance that we could see them out there coming. We'd see them on the way. And that chance is higher the lower the number of hard steps is, the lower this power is. And so that might be one reason to think the power is higher, is just to say, well, we don't see them coming, so either their speed is really high or the power is high. But actually, I have some other reasons to think the power is high. But why don't we put that off? First, I want to convince you that it is a power law. I mean, once I've convinced you it's a power law at all, then you're in my family of models here, and then we can just dicker over specifics like the speed of expansion or the actual size of the power. But until you believe that this power story, you don't believe any of my story at all, right?
Okay.
Okay, so what's the power? So the key idea is we have a sequence of steps that all happen to happen before a deadline. And so the chance that all of the steps happen before the deadline is the chance that each one happens with a short enough time that it can fit within this deadline. So I guess I should share the screen here again. I'm going to give you a little more mathematical taste than...
In the meantime, so we're 13.8 billion years into the universe age. If it goes for if the universe is able to create abiogenesis around the place, then we're still like about 550 times the amount of time we've already been in the universe left for there to be new civilizations born, or abiogenesis.
Right. Now, there's things to argue about. Well, maybe the rate at which new stars would form gets less, and maybe the rate at which, the kind of things that are left over aren't as friendly because they're around smaller stars that have bigger flares or things like that. But this t to the n factor really pushes it. If it was just a constant probability per time, it would still be puzzling that we're this early. But if it's, say, the time raised to the power of 10, then it's crazy unlikely that we would be this early. Because, it would show up, toward the end of the period that was possible. So to explain why it's t to the n, I'm pointing you to this diagram. So this is saying that 3 times have to be less than this deadline t. And it's showing you a diagram in 3-dimensional space. This orange volume is the volume of all these 3 times that added together are less than this time deadline t. So when we're asking what's the chance that each of these times happens fast enough, we are asking what's the chance that the point is in this volume. And if these steps are really hard, then we could have the density of the probability within this volume just be uniform across this volume. Basically, the chance wouldn't have changed much across the time. And it would just be a constant per time chance of any point in this volume. And so you'd be just integrating this volume. But still, integrating this volume will go as the power cubed of this time, is the key point here. Because we're basically integrating in 3-dimensional space. And this generalizes, so if we have n steps that all have to fit in, then we integrate over this n-dimensional space of all the step sizes that all added together are less than the deadline. And again, now we're going to get an integral that's proportional to this capital T raised to the power of n. And this is relatively robust. So it's not just that we're making this strong assumption that it would have to be this constant probability. It actually turns out that any power law whatsoever of the chance of getting to the next step after the last one as a function of time, any power whatsoever also gives you the same t to the n dependence. So it could be, a power law that declines, a power law that increases. And so that allows you for a wide range of step difficulties. So first of all, it's t to the n if each step is a constant in time step. It's also t to the n if each step is a power law function of time. It stays the same form if we add some what I call try-once steps instead of try-try steps. A try-once step is something where you just have the first try at it, and if you don't succeed, you just fail and fail forever, and you never get to try again. And in addition, if you have like a set of oases that appear at a constant rate in time, instead of all showing up at the beginning, you still get exactly the same t to the n. You integrate over the t to the n for each, and that ends up with t to the n total. And you can even have a distribution over their time windows and when they end, and if that distribution ends at a power law, again, you still get the same t to the n power law.
So what's an example of a try once? Now, I think you mentioned in a blog post that the creation of like DNA as a
well, it might be the code. So as you know, biological life has a bunch of standards that basically all life satisfies. It has a certain way that DNA encodes and translates to proteins. It has a certain kind of energy molecule that's used to transfer energy. And these standards are standards that life conforms to. Once most life around you has these standards, then it's in your interest to conform to these standards. Like if you want to eat them, then you want to have them have the same kind of chemicals, energy chemicals you use that you eat, for example. And if you want to have sex with them, you want to have your genetic code matched with their genetic code so you can exchange genes. And so early in life's history, we set on a number of these standards for using DNA at all, for example, to code for our proteins and having a certain mapping between the DNA and the protein units, etc., which are the fundamental units of proteins that are then used to build larger proteins. Those are all standards that could have been different. And it might be that had we fallen into some other standards, our sort of life couldn't have evolved and we would never be here. And so those are possible try once steps where some area just had to fall into the right equilibrium, the right sort of standard, and then from then on it stuck with that standard. Okay, so I've tried to convince you that this power law dependence is pretty general. It's not just one particular mathematical model. It's a wide range of models all share this feature, that the chance of passing through a number of hard steps by a certain time deadline goes as that time deadline raised to the power of the number of hard steps. Mm-hmm. And if that power is high, then that's going to concentrate the appearance of aliens all within a relatively narrow time from each other, where basically the universe is empty for a long time and then they all show up at once. And when they all show up at once, some of them show up really close to each other because, again, there's really this high probability of showing up in the last gap between two civilizations meet. A third one shows up right between because that's where the probability is max. So now I've sort of walked you through sort of the basic model of saying, well, the key idea here is we are early because there was a deadline. The deadline was set by sort of the average rate at which alien civilizations show up. We had to show up before they took over the space we're sitting in. In principle, that time to reach lots of civilizations could have been arbitrary. It could have been 1 million years or 1 trillion years. But the fact that we showed up now gives us one data point that says we are somewhere in that distribution. And so we can reasonably use 13.8 billion years as somewhere near the median of the distribution of when species show up. And then we can guess that the speed of expansion is going to be somewhere, near the speed of light. And the last part of the model we need is just this power. And once we have these 3 parameters, we've got the whole model, which says with mathematical precision a distribution over how far away are the aliens and when will we meet them? And maybe even can we see them? And again, this last part of the model you might wonder is, okay, why should n be high? And if I can't convince you of that, I could still convince you that this overall model is plausible, and therefore it gives us a reason to, guess how far away they are. But then they're basically going to be farther away. So the lower is these number of steps is, the farther away are the nearest aliens, and the longer it will be till we meet them. But it still roughly tells us how far away they are. So, this model tells us they are not 1 million light years away. The galaxy isn't teeming with them. The galaxy doesn't even have one other one, because the galaxy is only, 50,000 light years across. And, here, the 10th percentile in this simple one-dimensional is at least 30 million light years away, 30 million years till you meet them. So that we're talking clusters of galaxies, big filaments of galaxies. So actually one of the main structures in the universe is these filaments of galaxies that are about 50 million light years long. And so we're talking about the nearest alien being farther away than that.
Wow.
So they're really far. They're not anything. They're not in our galaxy or even in the nearest 100 galaxies.
But they could
far
be
away.
in our supercluster.
Perhaps. I mean, if I don't know how big our supercluster is off the top of my head, but if it needs to be at least 50 million light years across before that would make sense. So, this is telling you that eventually we will meet aliens, and there will be a long period of time, say from 1 billion to 100 billion years from now, when we will interact with aliens and they will matter for us. And of course, we may compete with them, and we may not exist after the first 2 billion years if we don't succeed in our competitions with them.
Just by way of just a note that our supercluster is about 100 million light years across. And it's
right, so that says maybe
they
they might be in our supercluster, but probably not. But again, I hope to get better analysis in 3 dimensions and larger data sets, and maybe that'll push the numbers closer. So we'll see. But at the moment, this is the best I've got. Sort of an average separation of maybe 1 billion light years, and maybe, the closest, if we're lucky, that 10% of the time they'd be within, maybe 30, 50 million light years away. Okay, so now we have the question of how many hard steps are there? Now, this whole model of this power law actually goes back to Brandon Carter, who had an article in 1983, which is almost 40 years old now, in the Royal Statistical Society. And I was just looking at it a few hours ago. And he talked about this idea that there's a bunch of hard steps the place like Earth has to go through, and there's a small chance of getting to the end before the deadline, and that implies this power, T to the N power law. So he had this 40 years ago, and many people have published on this since then, and I don't think anybody has strongly disputed this basic result. People have argued over the years, though, about how many hard steps there were on Earth in this period, and there's a couple of key data points that are relevant. So one thing we can say is, if there are many steps of different difficulties, we can classify them into hard steps and easy steps and sort of in-between steps. So hard steps are the ones that take longer than the time window on average to complete. Easy steps are ones that take substantially less than the time window to complete. And intermediate steps would be steps where they're difficult, they have somewhere near 50% chance of completing in the time window given. So easy steps basically just add a time delay. Easy steps just happen. They take 1 million years or 10 million years, and that just moves the origin. So in some sense, the more easy steps there were, or other time delays in our past, then we've had less than 13.8 billion years to show up. Because maybe some 1 billion year delay process just had to burn through before the next thing could happen. But these easy steps and delay steps would just, reduce our time origin relative to that start date, but it still leaves the T to the N model the same after that start date. Steps that are right in the middle are basically, it's like a power law, except the power changes over some scale, so it doesn't really change things that much. And so then the question is, how many of these hard steps are there? They're the things that set the overall difficulty. They set this power T to the N. Now, one thing Brandon Carter noticed 40 years ago is that these steps will all happen, and then you'll reach the final point before the deadline, and there'll be a period that you will have arrived early before the deadline. You won't arrive just the moment before the deadline. That's unlikely. You will arrive, in fact, if there's n steps, you will arrive about 1/n of the window before the deadline. So we have, say, 4 billion years so far. If our deadline was 5 billion years, say, then we would have arrived now 20% of the way before the deadline. And so that would be most consistent with there being, say, 5 steps. Or 4 steps, basically. Because, each step took about 1 billion years, and then you have this remaining time in the window of another 1 billion years. But, there's a lot of randomness in these times, so it doesn't have to be exactly 4, maybe 2 to 6 or something. But that's one key data point. But another key data point is the time of arrival of life. So if life started on Earth, and then the very first step was the simplest life showing up on Earth, then we in the fossil record see life showing up on Earth by 500 million years after the Earth seemed to be cool enough to support life, which is pretty short time. And that's a maximum. It could be much shorter. All we know is that the earliest fossil we found might be at most 500 million years after the Earth was fine. It might be much less, and that's actually getting to be a bit of a conflict. These are the 2 steps that are the most clearly going to be hard steps. The last gap before the window of life closes and the very first origin of life. And they're getting to be pretty different in magnitude. They're supposed to be drawn from the same time distribution, but in fact, it might be, in fact, there's another 1.5 million years of life available in life on Earth. People aren't quite sure about how long that window is. And so 1.5 million compared to sort of less than a half is getting to be a big ratio. So then there are other things within the last 4 billion years that people think might have been hard steps, but it's harder to know. Everything that's happened in, say, the last 500 million years probably can't be a hard step because they happen just too fast. So, everything you see in the fossil record of animals getting more complicated and bigger tongues and bigger brains and everything else happening, that seemed to happen at a relatively rapid clip. And so it's just not plausible that, those are steps that had the same expected duration as this time remaining that we have of 1 billion years still. And so those would be more delay steps. And there might have also been a delay step, say, with, filling the atmosphere with oxygen or things like that. We don't know. And so there plausibly some delay steps, but there might have also been some other hard steps. We're not sure. So originally, Brandon Card's article 40 years ago, he said, I thought there would just be a lot of steps. That's what he thought of looking at biology, and that's what I would think intuitively too. And he was surprised that this argument that we only, this remaining window has to be about 1 over n suggests that n is so low. And he, in an original paper 40 years ago, said, well, maybe n is only 1 or 2. That was his best guess. Only 1 or 2 hard steps. 10 years ago, he wrote another paper follow-up where he said, I think it's about 5 or 6.
Do you remember the name of the paper?
I have it here in my window, and it says 5 or 6 in the title. That's actually the title of the paper. Says 5 or 6 Step Scenario for Evolution. That's the title of the paper by Brandon Carter in 2008, International Journal of Astrobiology.
Is this the Australian theoretical physicist?
Well, this location was France.
Okay.
But I don't know where he is now or where he's been. But
he's Elmarker is University of Cambridge, so it's not in his.
Okay. But in any case, so I do think that there's 2 reasons to think that there's many hard steps. One is you just seem to see a lot of things happening in history, right? The small number of steps model says that things basically stay about the same until you make this next breakthrough, and then that's the change. But the more change you see that seems to be, positive and progressive, then the more hard steps you'd guess. And the other thing that makes you think there might be more hard steps, I think, is just to say, look how complicated the earliest life we've ever seen is. It sure is very complicated. It looks very subtle. It looks very sophisticated. And so the recent sort of hard step developments we might think of as, say, the introduction of eukaryotes and the ability to do multicellular animals and the introduction of more sophisticated sexual selection, those are definitely big developments, and they might have been very unlikely. But if you look at the machinery they take, it's a modest amount compared to just the total complexity of machinery of a living cell. Cells are just complicated. They just got a lot going on. And that, to me, says, well, there probably had to be a lot of hard steps to produce all that complexity. And that's why I might think there would be a lot of hard steps. And so, in a recent post a couple weeks ago, I said, well, this pushes me to say that maybe life came from elsewhere, the Panspermia scenario. But before we get to that, there's 2 other pieces of data which say that don't fit very well with this hard step model. So if we just say, looking at Earth over the last 4 billion years, we can look at these time spacings within Earth, but we can also look at Earth and its features. So the hard step model says that the chance of something appearing by a deadline is proportional to t to the n, and that really rewards longer lived planets.
So just for reference, that was the Searching for Eden post you had on your blog.
Yes, right. So this t to the n, figure of merit for planets producing, advanced life has to enormously reward planets that last a long time, because that t to the n is huge. So the fact that we're on a relatively short-lived planet, because our sun is short-lived, is kind of weird. And of course, the fact that we show up early is also weird, but we're explaining a different fact in this model. And another thing is, if what's happening in trying is there's just a big chemical soup on a planet and it just has to find the right chemical combination somewhere, that rate should then be proportional to its volume, or volume times metabolism, per volume, basically. The bigger the planet and the more activity there is, then the more chances it would have to find the next combination to go to the next point. So that would reward big planets. Big planets with lots of volume for life to be in, and then lots of energy to run off the metabolism. And Earth happens to be small. So there are these water worlds out there. There's gas giants, but if you look at things that aren't gas giants, actually about half of them are big water worlds with mostly water. And we're just on one of the rock planets that has this thin layer of water on the edge. And so all our life has to fit into this thin layer of water on the surface. And, we're really constrained volume-wise compared to a lot of the other planets out there. So this theory doesn't predict Earth very well at all when we're looking at sort of the metabolism or times the volume, nor when we look at the lifespan. So,
just as a note, some people argue that it would be very hard for an alien civilization to reach technological maturity on the water world because water is conductive.
Okay,
things like electricity might be hard.
So if life had to start on Earth and go through all the phases till where we are now, then you might say, well, Earth needed to meet a bunch of constraints that only really apply now when we are sort of technological or fragile multicellular animals. So, for example, people have said, well, Earth had to be a place that had a relatively constant temperature and constant orbit. It had to be far away from supernova. It had to be far away from solar flares. A bunch of constraints like that, because complex multicellular life doesn't do very well with supernova. It doesn't do very well with large temperature variations. It doesn't do very well with solar flares. And, and when we need to get to technology, if you're in a big water world and all the metals are down on the rock at the center of the planet, it could be a while to develop technology that lets you leave the water world. But if we think of panspermia, that is, life started somewhere else, these constraints get a lot weaker. So let's think of the advantages in the context of this model of panspermia. If life started somewhere else, then that somewhere else could be where the simplest life evolved, and that somewhere else could be fine with solar flares and a water world and supernova and big center of the galaxy explosions and flares and all those other things, because simple life is much more robust to all of that. It's our sort of complex life that has trouble with that. So, and of course, this first world of Eden that before us could have been much larger in order to get this figure of merit. So under this scenario, most of life's evolution happened on this other place, but then it had to come to a place like this because only a place like this was safe and constant enough to allow multicellular life and to allow civilization. In addition to these advantages, we have just the adding of the time. Remember, we have this time to the end. So if you just added one time length equal to Earth's time length as a previous time, then the total probability goes up to that doubling to the n power. So if n is 10, that's a factor of 1,000 favoring the hypothesis, where we have twice as much time.
So most of the difficult steps in evolution, you mean? Like before you said most of the evolution could have appeared somewhere
Most of the hard steps could have happened in Eden, somewhere else, wherever we came from. Now, obviously, the hypothesis that life started in Eden, went through most of the hard steps, and then came here gains these advantages because Eden can be in more places and it can be bigger, and it gains the advantage because now there's more time. But it does have the disadvantage that it's not certain that life could move from one place to another. So if life was enormously hard to go from one place to another, then that would reduce the probability of the scenario so low that it wouldn't be very likely.
Nature's von Neumann probes.
Right. But it seems like life started very early on Earth, and more plausibly, as long as life started early on Earth, the plausible place it could have started is in this stellar nursery that Earth shared and the Sun shared with, tens to thousands of other stars that were all in the same molecular cloud that collapsed to produce all these stars. And it could be that life seeded those clouds, which then spread life to all of the stars in that 10 to 100 to 1,000 star cluster that all were born at the same time. Our sun was born in a set of siblings of 10 to 1,000 other siblings all born at the same time. So in this scenario, then, the other Eden had to seed this cluster, this molecular cloud that was about to give birth. But that still could have been hard, and it would have had to come close enough, and there's chances. It's low chances. But again, we've got these difficulties of it all happening on Earth. So to believe it all happened on Earth, we have to believe that the initial origin was unusually early, and the time we have remaining left is unusually long, and we just happen to be unusually small, and we just happen to be on an unusually short-lived star. And all these things just happen to be unusual, but still it all happened on Earth.
One of the intuitions that comes to mind is the smaller the life of the planet or the star around it, would that select for faster evolution?
No. It would select for conditional on achieving some gain point. You had to do it faster because you had a shorter deadline. Mm-hmm. But setting aside that short deadline, it doesn't mean you do achieve it faster. It just means you have a less chance of success. Right? I mean, if you give a worker a job that would take on average 10 hours and you say you have to do it in an hour, conditional on him doing it in an hour, then it'll be faster. Probably you won't get it done in an hour and you'll just get nothing.
Fascinating. And so where do we go from here? I mean, that's a lot of information. It's really fascinating. I mean, it's mind-blowing. I'm still digesting it myself.
So there's two directions here. One is, how will we verify this, or how will we become more confident in it, or what sort of details should we work out? And the other is, what does it imply? So that second thing is sort of easiest to talk through. If, say, we have a decent estimate of the number of hard steps and the speed of expansion, then we can actually get a decent estimate of the distribution of how far away the nearest aliens are and when we would meet them, and even what the chances we might see them, sort of depending on what speed of expansion they have, how far away to look for and what size thing to look for, where they might be. But most likely they're too far away to see unless we try really hard. So it might start out some observational program of trying to look for a certain signature because now you have a better idea of what you're looking for. You say, don't even look in the galaxy. They're 50 million light years away, if anything, and you should be looking for things that far away. And now the question is, you're looking for some roughly spherical expanded volume of some different looking region, roughly that far away, and you'll give some rough idea of how big that would be and what that distribution would be. So
similar
it would
to
set up
what these sort of aggressive alien civilizations would look like in the your burning cosmic commons thesis.
Sure, although that's more specific. So that had more specific assumptions than had more specific conclusions. Here we're just saying they will expand at some rate and be roughly a sphere. And we're not saying anything about how they organize that or achieve that or what's that happens inside. But if that was happening via a local competitive process, then the burning the cosmic commons analysis would become more relevant. It would tell you about, given the assumptions of that analysis, roughly how how activity is distributed in that sphere and what's happening at different points of that sphere. But from the point of view of observation, we just say there's going to be spheres out there about a certain distance away, about certain size. Let's look for them.
So what would astrophysicists be looking for? Just spheres of what? Light? Spheres of...
That would be a key question, activity. But, the key prediction is activity.
Spheres of strangeness, yeah.
Well, not just strangeness, but also strange activity, right? They would be doing things, so there would be different energy uses and different sort of even locking down of energy uses. Maybe, on the frontier you see higher usage, and then behind the frontier suddenly things get dark because they found a way to block off all the wasted energy escaping. And, but they would be doing something with that energy, and they'd be doing it at the surface of their sphere. They'd be expanding out, and at the surface they would start to reach things and start to do things with it. And, the simplest thing, they're probably taking apart stars and rearranging them into something else they find more congenial. Mm-hmm. And, figure or whatever that is, but yeah, it would be some sort of activity.
We think Dyson spheres, but that might be like a hand axe by comparison to standard today's tools.
Right. I mean, I'm sure eventually people would get into the details of this, but at the moment I would just say you're looking for spheres of a certain size of unusual activity and a certain distance away. And, later on we could do more. But then there's this consequence of saying we will eventually meet aliens. This is now part of our predictable future. This is part of our predictable descendants timeline. This is a thing that will happen. We won't meet them for at least 50 million years, say, and maybe not for 1 billion years. But we will meet them at some point.
If we don't go extinct.
Right, if we don't go extinct before then. If we can survive that long and expand that long. And then at that point, they will have been thinking of meeting us. They will have figured this out too. And we will come together at some point, and then we will each play out the strategy we have decided on. If we coordinate. So, of course, it could be that we expanded the civilization and then that we don't organize. That is, each little part of our civilization is on its own. And then each little part that meets the aliens, it's on its own and dealing with them. And they will do what they can. Or we might somehow have some more organized strategy. That would be a matter of how well we can organize over this time scale. But, if we organize a lot such that we limit our internal competition, then we may find it difficult to reinitialize competition so that we're ready to compete with aliens.
Uh-huh.
Right? And so that might be a reason to sort of keep and reserve at least some substantial competitive ability, even if we manage to create a United Nations of the solar system and then the universe in our region of control, where we keep the peace and keep everybody, away from certain kinds of competition. When we meet aliens, that, they may not follow those rules. And that's an issue, right?
So do you mean like a culture of competition within our civilization?
Well, at least some subset that maintains the culture of competition. That some subset that could be revived and respread when we needed it, because we might need competition when we reached aliens. We might at least need the threat of competition to convince them to settle to some peaceful outcome. We might want to make a deal with them and to try to make agreements that would prevent harsh competition at the frontier where we meet them. But in order to convince them to give us good terms, we might need to have the threat available.
In a previous interview, you've mentioned that once we reach a certain level of technological maturity, it's not likely that we'll go very much beyond that. And because of the, the constraints physics applies to us, and same would be the other alien civilizations we may come in contact with. Yep. So they may not be vastly superior to us.
Right. Even in 50 million years, it seems almost certain that they and we will both have reached sort of the limits of technology, and we would both be sort of fully capable of using our physical world around us to do whatever needs to be done. So these would almost entirely be meetings of equals, at least in terms of technology. But of course, they might not be equal cultures or equal habits or something, depending on whether we've allowed those to decay or whatever. So if we remain competitive in the sense that we are composed of many small parts competing with each other, then that would determine sort of what sort of technologies we had and used and how we played it out, and that might cause the burning of the cosmic commons, as we talked about before. If we organized and have some central governance of our sphere of control, then that could be many different things, and it might not be very suitable for meeting an alien unless we made the choice to make it that way. But so there'll be this time when we meet aliens and they would meet us, and then that might be, up to 1 billion years from now, and then there'll be another 100 billion years before we separate so far that we can't meet or talk to them anymore, where the exponential expansion of the universe from dark energy pushes us away from each other. And so that would be this era of interacting aliens.
Yeah, that would be very fascinating. And
in that era, you can expect to see maybe tens to hundreds of other alien species who each had a separate origin and separately grew up to be mature and fully capable, independent of all the rest. So you would get some sense of the distribution of possibilities. So like within any one civilization, it might have founder effects where it chose some initial way of doing things and then everybody just copied that, and that's the way it did forever, right? And you will never really know what those are until you actually start to meet aliens and see how they do things different, because they will have had independent origins.
Yeah. It's interesting to think that if alien civilizations cooperated or with their sphere of influence like double almost as soon as they practically met each other, if alien civilization A and B were roughly the same size, once they start to collaborate, then their sphere of influence very quickly doubles.
So, I mean, that would be with the question of what scale economies are there with respect to just size. So, I mean, for example, if you can say, after 1 million years we're so big, and after 2 million years maybe we're 8 times bigger. And what new things can we do when we're 8 times bigger than we couldn't do before, right? And so there could be some scale economies whereby just being bigger lets us do more things and lets us achieve more things per person just because we're being bigger. And in that sense, when you meet aliens, now, if you make a deal, you could suddenly be bigger faster than just by growing, by yourself. And so, but of course, you could also have conflict, in which case it might limit what you can do. You might have been able to do many things because you had peace internally and you managed the peace somehow, and now you can't manage the peace anymore, and you'll have to have conflict on the borders, or at least the potential of conflict. Mm-hmm. And we'll be really curious about all these other alien species out there and their separate origins, and so, we will be willing to listen to messages they send, and we'll probably want to send messages. We'll probably want some sort of mimetic influence where the nearest 100 aliens all heard about us and think we're cool. And so, these different alien species would send out messages to each other and emissaries to tell about each other, and then they would be vying for social influence, right? Each civilization, once it sees a nearest 100 alien species, will wonder, which of these should I be most try to be like? Which of these are the ones worth emulating?
The battle of the
some of them will be more influential than others, and you'll be wanting to be one of those more influential ones, and so you'll try to present a good face of you and your history. And so now they'll hear what came from you. They'll wonder, can I believe that? Is that true? And so one of the things they will do to learn about your history is to look for signals from the very beginning of your civilization. So you won't expand fully at the speed of light. So before they meet you, they will get signals from you. And the very first signals they would get would be the signals from your very beginning. And that'll make it hard to lie later on about your beginning.
I like that.
And in fact, if you wonder, can you believe your own history, you can probably believe what aliens reflect back to you from your signals that you sent out at the beginning more than you can believe your own records. Because your records may have been distorted by people wanting to push various historical stories, right? Here we are, we have our records, but early on we sent out light. Somebody's going to get that light. If they just reflect it back to you, we could get information about our early history that's sort of safe from the influence of intermediaries of ourselves since then. Mm-hmm. and we only have to trust them to reflect it back correctly. But if we send it in different directions and they all send back the same thing, it might be pretty unlikely they could have coordinated to lie about it from all the different directions, and maybe we can believe that.
I hope some future dictators are listening in right now.
But that's sort of an interesting issue about sending out information. That is, today we believe history mostly because it's too much trouble to go everywhere and plant fossils, for example, if you want to trick people into believing fossils exist. But once we've been living in an area for a long time and really densely using it, the sort of old records will be gone. All we have is records of old records. And then we wonder, can we believe those records of old records, or have they been changed? Just like today, even in a corporation today, how can you believe what happened in the company early on unless, there's a news article about it and that was recorded somewhere else, and your company managers can't go mess up with the New York Times' news article, so maybe you can believe that.
That's so funny. I'd never considered the idea that we may find our true history by meeting another alien civilization, which reflects back to us what the signals that escaped us before we started censoring them. That is...
It's a reason to meet them, and of course it's a reason for them to send the signals back, and of course they can piggyback whatever they want to say onto them. So if they want us to listen to something, they just have to mix up these signals with what they want to say, so we have to disentangle them and get them both. It's a way to get them to listen to you, right? Mm-hmm. You want your neighbor to listen to you, well then get a copy of their paycheck and put the note in the paycheck, and then when they open the paycheck, then there'll be the note, and then they'll listen, right?
Mm-hmm. Mm. Well, I mean, that does give hope for civilizations to try to be more ethical. If, they have this consideration in their expansion, if they think that they're not the only ones in their locality in such that they'll eventually meet them within the next 100 million years or whatever, then maybe they'd want to be good.
I don't think they're going to be just generically good. They would try to be usefully nice in the ways that they calculate would actually benefit. Mm-hmm. Just like today, we are nice to other creatures who have the power to hurt us, and we're not so nice to creatures who can't threaten us very much.
Right. So we kiss upwards and kick downwards, as they like to say.
Right. Well, if it's really far down, we just walk over. Don't even bother to kick. And so, you might want to present your image to the aliens at least as if you're attacked, you would retaliate and you would be trouble. But, you also want to be cooperative among these aliens.
Especially
at least if they help you, you'll help them back, right?
Right. If there's one of your alien civilizations and there's multiple of theirs, and they're all coordinating, you'd want to be part of the United Nations of alien civs, maybe.
Right. Although you'll want to, in order to have it give you a good treatment, you'll want the credible threat that you could leave if they don't treat you well enough. So, I mean, this is all part of the usual games in our world today, etc. But anyway, there's, clearly there'll be this interesting period. We can't prepare for much for it now, nor do we need to, but there'll be this interesting period from 500 million to 100 billion years where there's a lot of interaction and contact.
Well, in what important ways would this scenario, the game theories of alien civilizations meeting each other, be different from the smaller sort of sized game theories that we see playing out in the world today?
So I think one interesting thing about the long term of the universe is the difference between stocks and flows. Today on Earth, we mostly use a flow of materials from the sun. It flows in at a constant rate, and we use it up immediately or it flies away, and we fight over flows. We can grow crops on the land or put solar cells up, and even if we destroy a lot in our fight, the flow still comes. So even if we have a massive war and we destroy our cities and we destroy our buildings and machines, after the war, the flow of the sunlight is still coming in, and we can rebuild because we haven't destroyed the source of the flow. That's continued. We've only destroyed some temporary things we used as a result of that flow. In the long-term universe, we will fight over stocks instead of flows. at least a lot of the time, and that will make a big difference to the game theory of the long term.
That's
if you have a big war and you have
technology.
Well, say you have a big war and you have a big stock and you spend most of your stock in the war. Now, after the war, you don't have much left. There isn't much left to fight over because you spent it all in the war. So it'll be much harder to decide how much to spend at any one moment to protect your stock. So eventually, you see, you will take apart the suns and you can burn the suns at whatever rate you want, and they are a stock. You're no longer constrained to just accept the rate at which sunlight flies on you as the flow that you must accept. And so different aliens in different parts of our descendants will each have stocks that they control, and they will have to decide how to husband those stocks over time. Now, one interesting thing is, say if they try to do computation with the stock, you can get more computation done if you use it slower. So if you have certain sort of hardware that embodies computer and you have energy you can put into it, the more time you take per gate operation, the less energy it takes. And so you can just get more done if you go slower.
Sure.
But you still have the same stock you're protecting. So if you think about some sort of conflict, if you're each trying to go slow, if you go too slow, you might not notice that they sped up to try to come to grab your stock. So you want the ability to speed up quickly in order to resist an attack, even if when you're not being attacked, you're going slow. And so in order to notice if you're being attacked, in order to be able to do this thing, you're going to have some level of activity that you maintain as a way to be prepared and to watch out for and retaliate against an attack. And so this will limit how slow you can go. And I've even written on this in some blog posts before, that this is the fundamental thing that sets the rate at which we burn up the future. In principle, the universe can go on for trillions and quadrillions and, add on more zeros of years. It can just be this vast, old, cold universe. But in order for you to have stock that lasts that long, you'll have to use it slowly. And if you use your stock slowly and people around you don't use it as slowly, you might be vulnerable to them. And so you might end up with a competition where everybody has to go sort of fast in order to protect themselves. And then we just all burn up our stocks. And then that's the end. We've burned up our stocks. And even though there's trillions of years left in front of us, we don't have any stocks left to spend.
Well, that would be, I'm maybe wishfully thinking here, but that would be a good motivator to coordination rather than going to war.
It's a reward, absolutely. Although we've always had a pretty large reward for avoiding war. War has always been pretty destructive. And so if only you could make peace, there are huge gains, have always been large gains if only you could make peace. But of course the problem is, you have this large losses if you don't, and you're afraid of those losses, and you have to make credible threats so that you can discourage other people from attacking, and sometimes those threats go wrong. A lot of wars can be thought of as each side making threats that they hoped they didn't have to make good on, and then some random thing happens to make somebody have to make good on their threats, and then they're all stuck in carrying through with their threats.
So the extreme end of going slow, would you consider the aestivation hypothesis as sort of similar to going really, really slow? But that's more like sleeping and not using up.
Well, that is the same thing. I would say that is the same thing.
Okay.
So that argument was saying that you would get enormous gains by waiting only if you waited. And, as you know, I and some co-authors have a paper criticizing that, saying, no, you can use stuff now. And there's no penalty for using it now, except for the fact that you just get more by using it slower. So they were arguing that, if you just let it sit, then it was just worth a lot more later. And we say, no, it's worth the same later, but using it slower is worth more. So there's a difference between, they were saying if you have a certain amount of energy, then how much computing you can do with that is basically depends on what your temperature bath is. The lower the temperature bath is, the more you can do. And we're saying, no, that you just have a pool of neg energy and you can do whatever you want with it. But the rate at which you can do gate operations per neg energy does depend on how slow they go. So it's similar in the sense of it does say it's better to go slow. It's not saying it's better to wait. So their hypothesis says you don't want to shut off everything and just wait and do nothing until later. What we say is, no, you want to go slow, but you want to start right now. That is, the sooner you start, the slower you can go overall. So you want to start going slow right now and continue to go slow as long as you can manage to, protect yourself while slow.
Okay, so the ways in which you'd manage to protect yourself would sort of determine how fast you burn your resources in the most part. Right.
So there might be a surface area to volume ratio sort of thing where you say the larger a sphere that you're protecting, then at the surface of the sphere you need to keep up activity to watch out for intrusions, but within the sphere you can go slow. And therefore now that would create a scale economy. Well, we want to have this big cooperative sphere where we've all agreed to pay for protection at the surface so that inside the surface we can go slow. And of course, in 100 billion years, when the alien civilizations are spread apart, you don't actually need to protect yourself from anything outside of your galaxy group because that's the only thing anybody can see. So then the question is, do you have peace within your galaxy group or do you have conflicts within that scale?
Mm-hmm. So that's in about, 150 billion years?
Right.
Yeah. Okay. That's relatively a short time scale compared to the age of the universe we've got left before the heat death, right? So
yes, of course.
Most of our time.
Now, we have to admit to our listeners that, it's like saying the sun's going to burn up in 5 billion years. You go, well, that's not really soon. I don't have to worry about that now. And so, yes, if you're worried about the pandemic or global warming or other things, we're talking about vastly larger timescales. But there are people out there spending money on searching for aliens and people talking about aliens. This has been a long, topic of conversation and speculation for a long time. And so as long as we're all interested in talking about it, I feel it's a contribution to say, well, look, I've got a model. It's a simple model, 3 parameters. It's basically answers the question. And, we'll have to wait millions of years at least before we verify it. But unless we can find visual signatures out there of slow-growing aliens. But other than that, it's a big thing we wanted to know about for a long time. And it sets this time deadline. We want to survive long enough to see this, and we want to maintain some sort of ability to deal with competition and rivals, hostile rivals, that we could revive and enable at that point in time.
Is there anybody who's produced a robust rebuttal to this model of yours yet?
It's brand new. This is 2 weeks old.
Yeah. Yep. Hot off the press.
Just a few weeks ago, I had the idea. I worked out some simple math, worked out a little Excel simulation, and tried to think it through. And so I'm still struggling to get anybody to pay attention to it. So I hope one of your listeners will respond.
Oh, absolutely. Yes. I'm sure as soon as this interview
this is a topic that a lot of people talk about in a lot of different ways. So it's also one of those sloppy topics, I'm afraid. There are just topics on which people find it so fascinating and so colorful that they are willing to be sloppy, and they figure it's not a serious topic. I don't need to be careful here. This is one of those fun topics. And so people are often just in a sort of fun, sloppy mood about this. And so that makes it harder for them to take anybody seriously because, people aren't so careful. So I'm unfortunately sitting in that pool here where when I write something, people go, oh, somebody's talking about aliens. They're probably in this silly, sloppy mode and, it's going to be stupid. So why should I read it? So that's this larger bar. That's sort of the tax you have to pay for talking about interesting things. And so amazingly enough, in our world, the more interesting the topic, the less careful and serious people are about it. And therefore, the harder it is for anyone who has a result to get it to be heard because it's in this pool of all these silly, sloppy things.
You're at the risk of becoming a meme, Robin.
I may have already done so, but the question is how long it lasts.
It may be a good meme, and you may want that. Maybe a form of immortality. Who knows?
In this world, we can't really prevent
at the edge
that.
of their sphere of influence. Our civilization billions of years into the future.
So you're probably right that this needs a clever name for this theory, and I haven't come up with one yet. So if you've got an idea, I'm open. Obviously, I'm building on the great filter idea or the hard step model. So this is sort of, I guess the hard step model of aggressive aliens. So remember at the beginning I said I'm only talking about one kind of alien. So many people are always very eager to point out that it's quite possible for aliens to go other paths. I tend to be somewhat skeptical about those paths, but in this analysis I'm declaring that I'm only analyzing one kind of alien, the kind that would expand and preclude others from expanding.
Right. And so when most people hear the word aggressive, they probably think barbarians swinging axes or something like that, or, somebody with a machine gun.
If there could be a better word, expansive alien, perhaps. But I need them not only to expand, but also to preclude other origins. You see, because that's what sets this time limit on the origins, right? If they expanded but did not preclude other origins, then it wouldn't set a time limit. And the whole analysis is the idea you have a deadline. You need to show up before they do in your area. And that's how I can calculate when you show up. So I need them to be aggressive in that sense.
Just
to
aggressive expansions. Yeah, aggressive expansionists, you could call them, right? No.
Well, I could call it expansive, although that has another meaning in our language. Expansion just means like talks big. I don't mean that. They do have to, again, preclude others of their kind. That's kind of aggressive, and they have to take space, which is kind of aggressive. So aggressive is the word I have at the moment, but I'm open to other suggestions.
Yeah. So, I mean, what was the main...
Maybe Grabby. How about Grabby aliens?
Grabby aliens. I reckon that could... Yeah, that's...
Grabby, so they're going to have to grab stuff.
Could be, yeah. That could be...
Territorial, maybe. Territorial aliens. They want more territory, and they won't let you come into their territory.
That's right. Yeah. Well, was Brandon Carter the main sort of inspiration for this? What were the inspirations? I'm curious. What got you thinking about this 3 weeks ago?
So this is a follow-up on my great filter analysis. So the key input is to take seriously this t to the n. That's the big thing that I've done in the last month, is to look at that t to the n and say, oh my God, that's important. That's big. I think I knew about it 20 years ago when I wrote the great filter, because I read Brandon Carter's paper from 1983 and he wrote about it there. This t to the n result is that old that everybody's known about it since then. But I recently read a paper from some of my colleagues at Future of Humanity Institute, Sandberg and Drexler and a couple of co-authors, where they were doing an analysis of the great filter, estimating the probability of different terms and that sort of thing. But they mention in there that this t to the n effect means you kind of want to assume that life can't appear around red dwarfs, which are these very smaller, longer living stars, because this t to the n factor would really favor them. So they were just saying, well, I guess we should assume life can't happen around red dwarfs. And I went, no, you can't assume that. And look at this t to the n. This t to the n really makes a big difference. So that's what really started me to think about this t to the n. So first I started to think about it in terms of Earth's history and said, how well does Earth fit with this t to the n? And I realized it doesn't fit so well. Earth is too small. Its star is too short-lived. These timing events aren't that evenly spaced. And that pushes me to think about Panspermia. And so I can see that this t to the n really favors Panspermia in the sense that bigger, if Eden was large, if Eden had a high metabolism, if Eden had a long timeline, that it existed, that could really add to the probability of that scenario. And then, after that, I realized, well, in thinking about aliens, I could get this form. So this diagram I showed you with that yellow region, that's this key insight to say, look, the time gives you a distance. If you assume that you had to show up in time before the deadline of that region, and that region has a shape, and that shape, when you integrate over it with this t to the n, gives you a median, which could be identified with that point that defines the region, and that gives you the spatial distances. So, and then thinking about that more, you realize, when the power is high, those distances are short. And you say, wow, aliens might be only 50 million light years away, even though, we've been around 13.8 billion years because of this, we all show up near the same time thing.
Mm-hmm.
And so it gives you aliens sooner in time and closer than you might think. Just if this wasn't a power law, if this was just linear, you'd say, look, we've shown up about 13.8 billion years, so that must be about the average time. So that's probably the average distance to the nearest aliens is another 14 billion light years away, which is like crazy far, right? It means maybe we'll see a couple of them before we separate so far we never see each other. If it was just t to the 1, you see, t to the 0 really.
Yeah. Yeah. We've only got one data point of life, at least origin of life, that we're going off. I mean, you've already admitted this, but that's...
Right, but I'm taking it as the data point of when we reach the potential to become an aggressive alien civilization. Now, we may not do that. If we do it, we'll do it soon.
Sure. Yeah, exactly. But if you... just finding another... evidence of another abiogenesis apart from ours, would that update your model? Let's just say we found life on Mars that had a different signature to ours. DNA signature or from a different
that would tell us more about where the great filter is in our history. So there is this great filter that is somewhere in our past. The universe started out dead probably, and then eventually it went through a number of steps to reach where we are, and then we hope to go through more steps to reach this visible civilization. And so the filter of interest, the total filter of interest, is the total filter from dead matter to becoming this aggressive alien civilization, which we aren't there yet. So we're very interested in where this total filter is. In particular, we're wondering how much of it is ahead of us versus behind us. And so the more likely we see anything that happened behind us in time in our order, then we will lower the estimate of how difficult those earlier steps were, and therefore have to increase the estimate of how difficult the later steps are. And so that means it's kind of bad news about our future potential. If we see something in our, something else out there that seems to have an independent origin, that achieves some point along our trajectory. Now, like I said, the most plausible place, if there was panspermia, the most plausible place for that to happen would be at the very beginning of the solar system when we had a bunch of star siblings. And so if life was spread in that early molecular cloud, it could have been spread to our other siblings. And so under this story, that would be the most plausible place to look for alien life, is to go out there. And they have very distinctive spectral signatures. That is, those other stars had the same mix of different gases in that cloud as we do. And so we've actually found one of them, apparently, one other star from our siblings, but there's maybe hundreds or thousands of them out there. But those might have then had the level of life that Eden had produced. And they only needed to go through what we've done in the last 4 billion years, and they may not, of course, probably have gotten as far as we have. But they could have gone partly along that step. So if we found those stars with something along our path, that could tell us something about the difficulties of the steps that have happened on Earth. But it wouldn't necessarily say anything about the difficulty of steps that happened on Eden before Earth, because we would share that origin with them.
Right. Given that it's only 3 weeks old, this hypothesis, and it's probably matured since, its inception. Is there any ways in which you think peers will challenge this idea? And if so, have you thought of any preemptive rebuttals?
I expect people to just complain about the t to the n, because that's in some sense the most complicated part of it. I mean, obviously you can say, our estimates are going to be uncertain with respect to our time rank. So for example, I would say the thing to do is to assume an equal probability for each of the ranks. Like there's a 1% chance that we're at the 1% rank, a 1% chance we're at the 2% rank, etc., up to a 1% chance we're at the 68% rank, and a 1% chance we're at the 99% rank, right? For each of those assumptions, that will tell you what the shape of this distribution looks like given the power and the speed. But, convolving that in does spread out our uncertainty because we just have this one data point. But, that seems a completely reasonable assumption, is to assume our rank, a uniform probability over our rank, at least until we have some other observations to exclude things. And then the speed of expansion, I think, it's quite plausible. It's within a factor of 10 of the speed of light. That is, aggressive alien civilizations probably could expand at a substantial fraction of the speed of light, so they probably would. And then the other
sails could go 30% the speed of light from memory,
for example. But of course, the problem is how far can they go? So with this sort of cosmetic expansion, they have to go a long way over a very long time. So basically, the devices that they're using that go a long way have to be very durable, very long-lived, very good at self-repair or whatever, because they have a very long journey.
And we don't know how much dust there is between galaxies.
And we don't know what weird things there are in between. It looks like it's empty a lot, but we don't know. So that's the hardest part.
Yeah. Well, you can use redundancy, but like, in another interview I did with Stuart Armstrong, we discussed as soon as we create a Dyson swarm, the power could be used to thrust the von Neumann probes at every star that we can see, every cluster that we can see.
But that's all to say, it looks like a speed near the speed of light is plausible, right?
Yeah, right.
Within a factor of 10 of the speed of light, right? So, now again, we could say, many people will say they won't want to, and we could just say, well, that's just part of the filter, right? What fraction of them choose to want to? So by definition, that's one of the tricks of, say, focusing on aggressive aliens. I say, I'm only giving results for aggressive aliens. I'm not giving you results for the others because, this is only a constraint on them. By definition, aggressive aliens, expand and prevent other aggressive aliens. Now, some aggressive aliens may also prevent other kinds of things, but that's harder. I can't say that from the model. That's not something I can derive. That would have to be an additional assumption. And the last thing is this power law. So now, I know many people get focused on all the other constraints. So, it is true that whatever made it possible for us to arrive is probably based on lots and lots of little constraints, like having a moon the size we do, or having a certain tilt of the orbit, or, there's all these physical processes that were relevant for our arrival. And obviously this T to the N analysis is abstracting from those, saying the net effect of all those is this T to the N process. And many people will say, but I want to hear more detail about that. And they may just reject this abstraction from those details. They'd say, well, I want to hear about solar flares, and I want to hear about how you get off a water planet, and, and they want a more detailed analysis of the detailed process by which any one place manages to achieve an aggressive alien civilization. And, in some sense, I'm just deliberately not doing that. I'm deliberately saying, I don't want to know all those details per se if I don't need to know them. I want to just have the simple model where that all averages out to some T to the N. Now, what N is, we're not so sure about, and we're never going to be that sure of, but I think, we can plausibly say N is somewhere between, say, 1 and 20. And that, narrows it down a lot.
Well, I just thought of a contender for the name of this. We could call it the Hanson equation. How about that? I've just
I can't do that, as you know. I can't do that. Other people could do that, but that's not
I've just called it the Hanson equation. I've looked it up, and I can't find one. There's nothing on... Well, I can't see anything easily findable on Google. So...
Right. At the moment, it's like hard steps to Grabby aliens. So... in the literature, the phrase hard steps is sort of, Brandon Carter started that phrasing, long ago, and that's sort of that connotes the more specific mathematical model of this sort of great filter process. So, this is in a sense a hard step model of Grabby aliens. Or territorial aliens, if you like. And that's the key thing is you got T to the N for them to arrive, and then they expand out at some rate, and that defines the volume in which others must arrive if they're going to arrive. And that tells us how far away they are because of the geometry of the space.
It'd be interesting to create a little poll. Not an authoritative one, but yeah, to see what people think.
I do polls on Twitter often, but I'm not sure what about the name or something?
Yeah, that's right. Yeah, so I suggested the Hanson equation because I don't know have you ever called anything else ahead? Well, of course you haven't.
No,
but I haven't seen anything. So yeah. Oh, look, this is so fascinating, and there's a lot.
In some sense, I don't have an equation. I have a simple model, and so the model is very simple, but it does require simulation to get the details right. So the way I simulate it, again, is say what I would do in a full simulation is I start with a 3D space, and I'd start with the actual distribution of galaxies as they actually are, say. Take an actual map from a simulation or actual observations, and then I pick random points with, which correspond to, say, random stars in this space, and for each one I then use t to the n to find a random time at which an aggressive civilization could appear then if it weren't precluded. And then what I do is I calculate precluding by taking the expansion wave out from each point and seeing which places an expansion wave from somewhere else would get there before it's supposed to start, in which case it can't start. So once you filter that out, now you have the space-time diagram of which things start when and expand to where and where they meet. And that's the model. So there's not much to the model, but there's not an equation that actually captures that map. That's actually a spatially complicated map, because remember, it has a lot of things happening in the crevices where they meet. Has this more of a fractal structure where they start in as scattered few places, but then as the t to the n really emphasizes the volume up near where two civilizations meet, and so things appear just before them, right in the crevices. And so that's a pretty complicated picture. It's not an equation, but it's a picture drawn from a relatively simple simulation.
So it's not somebody people get a tattoo on their back of, right?
Unless they want to draw that image or something, or maybe there's a way to write the code as a few line piece of code that generates it or something.
Sure. Yeah. Wow. I mean, like, have you had any? Are your contemporaries at the Future of Humanity Institute, Drexler, Sandberg, Bostrom, have they critiqued this, the latest version of this argument?
I've talked to one of them about it, but I haven't talked to very many people about this, and so this is new. And so, you are getting an early first coverage here of something new, which I think has to eventually become the dominant view, because it's just pretty simple and elegant, and it's hard, there's not much to disagree with. But this is an area where basically people are just not very careful or serious, and so it just takes a long time often for people to bother to pay attention to what people say in this area. Which is weird, because you'll see newspaper media willing to write stories about these things if they're high prestige sources, but if they're not high prestige sources, no. So it's even like AI or something. There's a lot of these topics of interest that a lot of people talk about. So many people talk about that news media don't know who to listen to. They know their readers are interested, but they know that if they quoted every person who talked about it, it would seem pretty silly. So they really focus on the most prestigious sources, and then they only give news articles about aliens from prestigious sources or AI from prestigious sources, etc. And then everybody else is, ignored. But that's how they deal with their
So the Neil deGrasse
too much information problem.
Maybe we need to set you up with a panel on a panel with Neil deGrasse Tyson talking about this. And hey, Neil, if you've subscribed to my channel, maybe you want to start talking about this, or give Robin an email or something.
I mean, the best thing to do would just be to have a relatively private conversation with people, go through it. I mean, when you put somebody up on a panel in a public thing and you confront them with something they haven't thought about, they're not in a very good position to work through it. So,
look, I've never. Well, I did speak to him very briefly about 10 years ago, but apparently he's quite approachable. If you can get in touch with him, Neil deGrasse Tyson.
Right, but just in general, most everyone has these heuristics that there are these topics on which so many people say so many sloppy things that they just can't be bothered to listen to random sources on. That's just a generic thing about most academics or intellectuals, right? So, like, most physicists aren't willing to listen to your theory about the foundations of quantum mechanics. Even if you're another physicist, that's just one of those topics, right?
Well, how do you market this? I mean, do you just say, hey, look, I'm trying to be intellectually humble here, but this is not a sloppy model. Please take notes.
I mean, the official thing you're supposed to do is to write up a nice paper and submit it to journals, right? Now, unfortunately, in our world, often they will just summarily reject it if it's on a topic that's too, sloppy of a general topic and you're not a prestigious enough person. But that's still what you're supposed to do, and eventually get it into some journal, and then eventually people will read the journal article and then maybe pay attention, right? That's how these things are supposed to work.
How
So obviously I should do that part of it.
Yeah, of course. Yeah. How successful has papers on the Great Filter been? I mean, you've already got a history of writing about this sort of stuff. It's not like you're unknown. You may not be Neil
But that's
deGrasse
not enough.
Tyson, but you've got a history.
Unfortunately, that's not enough. Which just so the way academia works is it's mostly about the prestige of the venue in which you published, and so even if you have published stuff before, if you haven't published in that field before, it doesn't. Stuff you publish in other fields usually just doesn't count. And so it's usually actually very hard to publish outside the field in which you know people and have credentials. And so, in fact, it's not just because they look at you and they say, who the heck are you? Or they can see that you're not from your discipline. Most academic writing is of a very distinctive style that signals that you're an insider. Most academic papers have to use the right format and the column width and the words and the way you do tables and what you cite and just the style of talking. To someone who's been in a field for a while, it's just painfully obvious if you're not one of them, because after they start reading, they can see you're not one of us. You don't talk the way we talk. You don't write the way we write. You use formatting this numbers the way we format numbers, and they just have a generic reaction, which is outsider reject. It's the easy, safe thing to do.
It's not that.
And so that's the standard penalty against cross-disciplinary work in academia, which is just general. And then once you write on one of these sort of topics, I mean, so even for my astrophysicists, right, if they get a paper on aliens, they're going to go, that's much more likely to be one of these sloppy idiots out there. Because, there is this work, I have a blog post from a long time ago basically saying, like, free thinkers are one of the main obstacles to innovation. Free thinkers tend to think, I am an innovator, and there are all these, conformist people who are preventing innovation, and I'm going to be a free thinker and go promote innovation. But what happens is when free thinkers are sloppy and they keep throwing out their creative thoughts that are sloppy, they create this reputation that people think, oh, stuff thrown out on the topics those people like tends to be sloppy and I should ignore it. And so the topic of aliens is one of those topics, a very, standard topic on which people are ordinary people who get excited just about something because it's interesting. They think about it or write about it or something, and they sloppily throw something together, and they send that to some academic who then goes, this looks pretty sloppy and stupid. Why should I ever look at anything like this again? And so that creates this obstacle to getting past that, presumption of stupidity, basically.
Right. And so maybe aggressive aliens is not going to survive as a title for this hypothesis.
I'm not sure the title will make that much difference, but you will want to convey, the journal article about this needs to convey the proper degree of seriousness and caution and carefulness and tentativeness of its thing. And, that's part of, but, that I can do. It's all the very specific norms of very specific fields and how they like to see things is something that it's much harder to produce. Mm-hmm. But just being generically careful and tentative is at least doable.
Yeah. Is there anybody who has a thesis similar to this, other than, Brandon Carter? So, I mean, he doesn't come up with the whole idea, but is there anybody else that has a similar thesis that you think is worth comparing? Is there any other competitive ideas that you think is worth comparing to?
Other people have said, basically, maybe we're first.
Yep.
And they've said that that's consistent with what we see. So it's not that, which is different than we're the only. Right? But, that's by itself hard to say much about, right? So if you just say, well, maybe we're first, then the question is, well, what does that say about when the next one will show up and where it will show up? Well, they have to show up after. Okay, but where, when? And, you need more structure to the analysis to be able to say more about where they will show up after. And then you might say, well, why would we be the first? Like, why wouldn't we be in the middle of the distribution? Well, you say, well, we look out, there's nobody there, that must mean we're first. But you could say, but isn't that pretty unlikely and weird that we would happen to be the first? You could say, well, since it looks empty out there, we must be the first. And you go, that's positing this unlikely thing. Unlikely things do happen sometimes. We have to allow them in our range of theories, but each theory should get a penalty against it the more unlikely things it needs to posit. And so, merely saying we are first and the reason we...
dark forest.
Right, so the reason why it's dark out there is because everyone's hiding is a different story, right? So you could say everyone's hiding has other penalties against it, but at least you're not having to posit a priori, unlikely event right from the start. I mean, the problem with everybody hiding is why don't if everybody's hiding for each other, isn't there an advantage for somebody to jump out and grab a bunch of stuff, early and fast and win the contest, right? But that's that has to go. I mean, that's not crazy. You have to work out those details. In my mind, the details work against it, but I consider that to be a completely reasonable theory to explore.
I mean, the more resources that you take, the more resources you need to burn in order to hide them. I imagine it's not going to be that easy to hide.
Right. Now, interestingly, the scenario I've just outlined doesn't require they be visible. The key thing is that they preclude newcomers. So the key assumption in this analysis is that your deadline is when their sphere of control reaches here, because after that they wouldn't let you arise. Now, there's no requirement that they be visible. But, of course, I do think that's somewhat likely, but that's a separate analysis. It's a separate assumption. So that's the choice here to say, well, the key definition is that they expand and that they preclude.
Yeah, expanding would cost, but hiding your expansion just seems to me as though it would be very difficult to do. Well,
if everybody's hiding, you see, and then you're not hiding, the question is, how vulnerable are you to them? So, in the simple scenario, you say, well, if everybody has these weapons that are really powerful that they can shoot at any one thing they see without revealing where they came from, then basically anybody who sticks their head up gets shot and everybody else stays hidden, right? But the question is, well, say somebody sticks their head up. You might shoot at them, but you think, why should I risk exposing myself by shooting? Why don't I let somebody else shoot? And you might have this free rider problem where you're worried that somehow by shooting you will expose yourself. And it's not crazy because you think, well, it's actually pretty hard to shoot at them in a way that hides where it came from. And what if they've moved since then? Now, if they stick their head up and stay in the same spot for a long time, that will make you more tempted to shoot at them. If they were sort of randomly wiggling around, that would make it harder because now you have to send something closer to them that tracks them and tries to hit them. Which is going to be more elaborate, but I think the strongest argument is just to say if everybody's hiding, then they can't be using that many resources because if you use a lot of resources, that tends to be visible. So they have to have small things out there hiding that have the potential to use more resources. And so you have to think, well, what if I start first and just start using a lot of resources so fast that by the time they see me, they're too small to do anything about me. That seems to me the best argument about them hiding and say that just works as a strategy. And every once in a while, somebody should try it. They should just try growing fast, and then as soon as they grow fast, somebody hits them and smashes them, and they go, oops, I guess that didn't work. But it wouldn't cost you that much. You go send a thing way out over there and have it try to grow over there and see what happens. Every once in a while, people should be probing this thing to see, could I get away with growing really fast somewhere? And you might have the same risk of that exposing you as squashing somebody else. So why should I pay to go squash somebody else if I'm not going to pay to try to break the embargo once in a while? See if I can get away with it.
So you do see the dark forest hypothesis is something credible.
It's a credible in the family things, but in the end, I reject it. That is, in the end, I can't make sense of it. But at least it deserved to be at the table of things to consider. It's not a crazy thing to just you throw off the bat right from the beginning. It has a surface plausibility that demands it be taken seriously and thought through. But I think when you think it through, it doesn't work.
Okay. What other theories do you think are plausible that are competitive? Do you think? that either fit in or...
Well, right from the beginning,
disconfirm.
we are completely alone story, right?
Yeah.
There is nothing out there, period, zero.
Yeah, you mentioned that, yeah.
Then at the other extreme, there's the zoo scenario. There's a big sphere around the solar system, and it's putting a movie screen and making us see things that aren't really there. And behind that sphere, there's a whole different universe that we're not actually seeing. In some sense, everything we can see is a nature preserve, and all the activity happens somewhere else we can't see in some dark matter, alternative universe, or, through wormholes or something. So some power has taken over everything we see and forced it to be a park, a wild park that, which little modifications allowed. And for some reason it's allowing us, but it won't, later on it just won't allow us to do much. So, in my analysis, I was assuming against that by saying, well, again, they would stop us if we became an aggressive civilization. So under the zoo hypothesis, basically, we would face pushback, strong pushback, should we try to become an aggressive alien civilization. They would just stop us. We don't know that they can't be stopped because we haven't tried yet.
Mm-hmm. So that's a plausible...
so that deserves to be on the table. That, still seems pretty crazy sounding, but yeah. They are out there and they are in full control. Some power is in full control of everything we see. And they have, for some reason, have decided to keep it in this nature preserve form. But they retain enough power to squash anything that tries to defy the nature preserve.
Right. And there'd be a good reason why they'd not try and just surround us with some sort of simplified universe that isn't as complex as what it looks like to us, or maybe it's way more complex than what this
those would be the two different versions of the zoo hypothesis. One is that our views are not reliable, what we see is just an illusion, that we're not actually seeing what's there. Another version of the zoo hypothesis is everything we see is exactly as we see it, and it's being forcibly preserved in that sort of natural state for some unknown reason.
What's more likely? What's your view? What's your favorite?
If they were going to put a sphere around the solar system to hide things from us, they could just put us in a simulation. I would think that we're in a simulation hypothesis has to be stronger than there's a light year sized sphere around us.
And
that just seems crazy expensive.
Right. Yeah, exactly. Yeah. But do you think that we are... what's your credence on us beating a simulation while we're on the topic?
Relatively small. We've discussed this before, I think. But basically, I think our interest in the past fades more quickly than does the number of people in the past. And so if that continues into the future, then they will make simulations of their recent past, but not all the way back to us so much. So I would predict a large integral over the total number of simulated people ever, but not that much of an integral over people like us. We're too far in their past to be of much interest. Because even today when we write stories and in video games, etc., we have very little interest in, say, people from 3,000 years ago. Who there were still lots of people around and they had big complicated lives. We have no interest in stories or games about them. Our efforts at simulation focus on much more close in time to people more like us.
So, the people who loom large in our imagination and, like Isaac Newton and people who've discovered a few interesting things, yeah, sure, they're interesting to us, but you don't think they'll be very interesting to people in the far future?
Well, a few people might be, but you and I not.
Yes.
So obviously the simulation hypothesis has to be, made specific to a particular person. Is that particular person in a simulation? Because it could be true for some people, but not others, right? Depending on how likely it would be that the future would simulate someone like that particular person. So when you say the simulation hypothesis, I'm of course making some sort of average over people like us and people listening to us.
So I don't think
could be they simulate Trump into it. Trump simulates for the next trillion years. There's always, because somebody writes a comedy about Trump, and so he's a character in a favorite comedy, and so people like to inhabit that comedy
So his
simulation, right?
representation his representation may survive. Sucks.
Right.
But yeah. He won't survive, hopefully. Yeah. Well, it's been, yeah. Is there any conclusive remarks you want to make about this thesis of yours, which I'm dubbing the Hanson equation?
I mean, basically, we could just notice how unusual it is for someone with a new theory or approach to sort of give an interview 2 weeks later to someone about it. We could just say to ourselves, gee, I wonder how that goes. I wonder why that never happens. And I wonder what will happen differently this time because we did this interview so soon into the process.
Indeed.
It's worth pondering why this hardly ever happens, but it does seem to hardly ever happen. So,
Wow. Well, I'm just about to go on a camping trip for a couple of weeks almost. I've got a lot to think about. I'll try and post this before I leave.
That would be nice.
Which will
and
be
so
in a
I guess
couple
you
hours.
can't be as careful with everything. And
Yeah.
I will send you the audio file, and then hopefully you won't need it. But if you do, then it'll be there.
Well, the audio file will probably be a better quality. But thanks everybody for tuning in, and thank you very much, Robin, for allowing me to be the first
Nice to talk to you
interviewer
again,
on
Anna.
this topic. Yeah. So,
Thanks for letting me talk about this.
Oh, absolutely. It's so fascinating. I'm just really happy to. Great. Well, yeah. Please subscribe, everybody, and definitely check out Robin's blog and read the posts which he wrote about this, and I'll provide links in the description. Cheers, mate. So, yeah. Speak again. Cheers.